In our last investigation, we saw how isolated hydrogen atoms baffled physicists by emitting light in distinct, sharp lines rather than a continuous smear. A second mystery was brewing at the exact same time, found in the mundane glow of a piece of charcoal or a blacksmith's iron. We all know the relationship between heat and color. As the temperature increases, the glow shifts in a strictly predictable sequence: red to orange to yellow, and eventually to white. It is a common, everyday phenomenon. But could classical physics actually predict exactly how much light comes out at every single color? To find out, experimentalists used a controlled environment called an ideal black body cavity, essentially an oven with a tiny pinhole to let a sample of light escape for measurement. This is the exact experimental data they recorded across every frequency. The curve is smooth. The intensity starts low, reaches a distinct peak, and then gracefully falls off at higher frequencies. The data was undeniable. Now, the most brilliant minds of the late 19th century faced the task of using classical laws to explain why hot objects produce this exact, precise curve. They approached the problem by contrasting matter and light. Matter consists of finite particles with a limited number of ways to move, but light is an electromagnetic field. When electromagnetic radiation bounces inside the cavity, it forms standing waves. It's the same geometric principle as plucking a violin string. Inside the box, the core geometry changes with color. Low frequencies have long wavelengths, so only a few simple modes fit. Higher frequencies have shorter wavelengths, allowing a drastically larger number of possible wave modes to fit into the same space. The count of these possible modes scales with the square of the frequency. As the waves get shorter, the number of modes explodes toward infinity. Next, they applied the principle of thermal equilibrium. In classical physics, thermal energy must be shared absolutely fairly among all possible independent ways a system can store it. This classical, baseline share of thermal energy is known as kT. This created a logical collision. If every one of those infinitely growing wave modes demands its exact equal share of energy, classical physics is heading toward a disaster. Lord Rayleigh and James Jeans were the investigators who combined these ideas: Maxwell's waves, standing modes, and equipartition. At low frequencies, their calculation matched the experimental curve flawlessly. But high frequencies contain many more modes. Since every mode still demands its kT share of energy, the predicted light intensity doesn't drop. It skyrockets endlessly. This failure is the ultraviolet catastrophe. Classical theory dictates that matter and radiation cannot reach equilibrium because the high-frequency radiation field acts as an infinite sponge, demanding all available energy. According to these laws, looking into a warm oven should blind you with an infinite blast of high-frequency light. The fact that it doesn't meant classical physics was broken. This was the mechanical problem Max Planck tried to solve. He needed a way to stop those infinite high-frequency modes from easily absorbing all the thermal energy. He realized the problem was continuous energy exchange. Planck made a radical assumption. Smooth energy exchange between matter and light is an illusion. Energy can only be traded in discrete packets. But a fixed size wouldn't solve the catastrophe. The cost of an energy packet must increase directly with the light's frequency. Because high-frequency light is now too expensive to produce at normal temperatures, those modes remain unexcited. The math perfectly recreates the falling curve of the actual experiment. Before Planck, physics related wavelength to frequency. Planck established the very first fundamental bridge between energy and frequency. Planck believed this was just a mathematical trick for glowing ovens. But this new rule would soon solve the hydrogen mystery from our last episode and convince a young patent clerk that light itself behaves as a particle.